Okay, now it's some better pen. Oh, much better. So on the unit circle, in complex plane, angle omega is right there. And that point here, e to j omega, is basically here. Like that. Good. So basically, the frequency response is the same as you evaluate the transfer function on the unit circle. And here we have the frequency of 0. Here we have the sample rate over 2, Nyquist frequency. And back here, this is also sample rate. It's right there. And this is basically symmetric, so okay, so most interesting part is actually the upper half. Good. This can be then divided into two parts for plotting purpose. I hate plotting that on the unit on the complex plane. It doesn't give me any. Well, some actually like it. Usually radio frequency guys like the plotting things on the polar coordinates, but I'm not a radio frequency guy. I'm a dinosaur kind of guy. So we have the amplitude response, which is the absolute value, amplitude response or magnitude response, depending on the vocabulary. And then you have the phase response. Like that, which gives the phase shift of that frequency. So this part here is the phase response. Okay. So usually you actually have two graphs. So amplitude response, especially on the MATLAB, when you do the frequency response of the system, it gives you the amplitude response. Okay, something like that. That will be a low pass filter up to Nyquist frequency. Okay, and preferably in dB scale. So attenuation in dB. And then another graph for the phase response, where basically this part is interesting. The passband is the interesting part, and then the interesting thing there on the phase response is I draw that one a little bit funny, since usually you don't have advanced phase response, but negative phase response, meaning the signal will be coming after. So that part, if the system has linear phase response on the passband, that's very good property if you are having a say some data transmission kind of thing, or it could also be nonlinear. Okay, so phase response is, the amplitude response is kind of easy cake. The phase response requires a little bit of more of the writing. Maybe I'll do it here to make it, really messy. Okay, so we are talking about phase response. So for real life signals, we have say signal is, or let's mark it x. Xt equals amplitude times sine of omega t. Then that one goes through the system. h of s, what comes out is the A times the amplitude response. Well, this is a little bit mixed kind of thing. Actually, amplitude response for real life signals would be something like that, physical scaling. And then the same sinusoid plus the phase response. Okay. In case our phase response is linear, meaning if this one is same as a constant times omega, it basically means that that part is sine of omega times t plus k, meaning that if you have a linear phase response, then the time delay through the system is constant. So basically, if you have a system with multiple frequencies and you want to, as a carrying information, you want those packages to come at the same time out of the system. For example, a dual tone multiple frequency. The filter bank to actually get the, even the faintest data out of the signal would require quite linear phase response to be able to do it. Okay, so for that reason, the linear phase response is important. Then actually there is the definition of group delay. Group delay is simply the phase response derivative to omega, and that is the group delay. So basically, if a group delay is constant, then we have a constant time shift. So that is a time shift versus frequency. Okay, there we have some responses. So we have a frequency response, which is simply transfer function evaluated at unit circle, where this complex angle actually gives the physical frequency. It's directly proportional to the physical frequency. Then this one is complex number, but for plotting, it's good to know what is the amplitude response, meaning what kind of is this low pass, high pass, how much it has the stop band attenuation and shots. And then the other part is phase response, and for if the system does not allow much of distortion on group delay, meaning if the group delay must be about constant on the this passband, then you need as linear as possible phase shift. Okay. Tomorrow we'll take a look at FIR filters, which basically you can make those easily linear phase response systems. It just requires some symmetry, and that's it. Okay. I kind of skipped one thing. How about this impulse response? Impulse response basically will tell you if the system is FIR or IIR. Only thing what you need to do is to observe the impulse response, and does it end or not. So if it ends, that's FIR. If it does not end, then it's IIR. And how fast should it end? Well, if this is nth order system, nth order system, then basically you just wait until the nth delay. So that will be a nth delay of this one. So after that one, if the system impulse response is 0, then the system is finite impulse response system. If you have anything after the order number, then it's infinite impulse response system. Okay. So the order number actually gives the maximum delay also on the FIR systems. Good. So all of that you can get by evaluating the impulse response. In MATLAB, our system actually, the system implementation is the filter BBAA, and then delta in would give you the impulse response. There. Frequency response like that in MATLAB is frict. I have no idea if I can actually use it today. But if not, I will just use the octave to show the general idea. Group delay, I think there is a also a function for that one, but that's actually also easy to kind of measure. The group delay in MATLAB would be filter the phase shift with 1 minus 1, 1, and phase shift, and divided by delta F. Yes, delta F, which is Fs divided by number of points. Where's the Fs? Oh, wait a minute. No, wait a Ts times that one, I think. Yes, of course it is like that. Okay. Good. So that's the first part. The other part of today's exercise is about making the spectrum. Human zoom. Second part was the spectrum. You have a question? Yes. The frequency response, or what? Yes, for example, okay, this is for system, the frequency response. You can actually also use that one to do the frequency analysis of the system, but generally it's the system coefficients, and then it actually plots you this the amplitude and phase response of the system. Okay. Yeah, that's messy. Let's take out the evidence. There we go. Then about the spectral analysis of signal. So if we have a time-based signal, I think I will just continue that one later on. And want to know what kind of frequencies we have on that section of the signal. What you need to do is just to do the Fourier transformation. I will actually mark this one with X, and since we have the sampled signal, and then if you do the discrete Fourier transformation, you will get the spectrum. Okay. Actually, doing the discrete Fourier transformation would be wasting the bandwidth, and which means energy we should conserve. So we use usually FFT, fast Fourier transformation. You have taken a classical digital signal processing class, right? Which means that you have heard about Radix 2 kind of implementation of this fast Fourier transformation. Who cares? I don't. I'm just using it. It was science in 70s. Cooley and Tukey made a really wonderful discovery. On 80s, it was already a tool, but we still actually had to write this kind of how you divide those into even and odd parts and that kind of things, and it wasn't fun. Will be engineers of 2020s or something like that. So just use it. Don't make this as a science. It's actually a really nice piece of engineering. But anyways, when you do the discrete Fourier transformation, on that block, first it means that you must have the n is 2 to the power of something. So that many data points in order to use the FFT. If you have less, basically you can do zero padding to achieve the same resolution. So it's basically what this one does. It maps the this data into frequency components between 0 and sample rate. Equally same amount of samples in frequency space. And there's something funny. That one is above the Nyquist frequency, but you need this one because, well, it's the kind of the negative frequencies. So in principle, you have this kind of the frequency of the spectrum of discrete sample is actually it's periodic. Okay, and the fast Fourier transformation maps this into this, and the only part what we are interested in is actually this part from 0 to Nyquist frequency. Okay, so basically the index for the middle point is n over 2 plus 1, because this 0 frequency is on the first element. Okay. Couple of other things. You have heard of windowing, right? Windowing methods, or Gibbs phenomenon, Gibbs effect. It was mentioned on the just about 23rd lecture, or something like that. Gibbs effect means that if you have a real case, like we do always, real life case, this actually is mathematically the same as multiplying data with a box, which means that this one here is actually also covered with the convolution between this real frequency response, real spectrum, and that Fourier transform of the box, meaning sinc function, which basically tends to widen those peaks. So if you have one single peak, in reality, one single poor frequency, it basically goes wider when you have that kind of window, the square-shaped window. If since this one then gives you some trouble if you want to see very fine details on the spectrum that are between some of these, say, more intensive peaks. Okay, but if that is the case, then you would use some smoother windowing, which would give you flatter spectrum, but it goes deeper on those values. Okay, but more about that tomorrow. Today we are just using these rectangular windows, but we are not expecting to have really fine separation between different the frequency components. Today we are focusing on getting nice looking pictures. Okay. You know, when you start doing the engineering profession and you need to prove your things to non-engineers, make fancy pictures. Seriously. Make nice pictures that look very professional. Use colors and such kind of things. And then on the business side, the S-curve. Okay, remember the S-curve. All right, so, but anyways, now we have one single spectrum. But how about our data usually goes forever and the spectrum changes? One good idea is actually start making the kind of image from this whole mess, and well, how about this kind of image? How the frequency components change over time. So we have the frequencies axis on the vertical axis and time axis here. And we put the data this way. Easy. Well, image. So you can actually highlight the higher frequencies. So you do each of these columns would represent one single spectrum. So that's the first spectrum right here, and have the highest components maybe somewhere here. Then you take another part, not here. That's the third one, since I want some overlap to increase the time resolution. some overlap. So so basically, for example, the n divided by too much of the overlap between subsequent samples. And there we have some different frequencies and maybe something like that, and then it can drop. That way. So we have a image that shows the most important characteristics of spectral characteristics of the signal, and this is called spectrogram. The bird watchers, ornithologists, they have those kind of spectrograms on their books, I have seen. But that's so nerdy and geeky stuff. I would never go, bird watching. Never. Yes, I have done it secretly. So, yeah. So the spectrogram can be actually used for recognizing that kind of, like bird singing or human voice or the voice recognition. The problem with the voice recognition on time space is that you cannot really use the correlation there, since even a slight change on tone will make these voices, sample voices, and this real voice look like totally random. No similarity at all. But on spectral space, if you calculate it as an image, spectrogram image, then you can actually start comparing with some modeled stuff. Okay, so that's the fundamentals of voice recognition right there. Okay. Picture. Then we'll take a look at what it looks like. All of this looks like in MATLAB or the competing software, depending if it works or not. All right, so there we go. I have MATLAB already running. So the first part was the impulse response. Just a moment, I'll check what we did yesterday. There, brute force of linearity. Okay, functions. Wow, we have done a lot. Hey, here I have a nice system. I can evaluate actually those F9 and roots. Okay. Nah. Modify that one. Okay, now I have my system, I hope. Oh, there we go. So I just actually evaluated. So now I have a system which is has the AAE same as this one here, and then BBN is the that one. Okay, just getting some system in. It doesn't matter what kind of system you take. So you might actually start typing the AA, those values, BB, those values. I'm just lazy. I used yesterday stuff. Okay, the frequency response showed, or not the frequency response. The Z-plane of that actually showed something. Maybe I should actually move into Octave, since I cannot otherwise. Octave is in. Okay, that's the octave. So it's not MATLAB, but somehow the usage actually resembles a lot of the MATLAB, and they are not competing. The MATLAB is used industrially and also in academics a lot. On academics, it has one small problem. It's a little bit pricey, but you have the MATLAB use it, since it comes with the really great package of toolboxes. When you get into the engineering position and you need some, mathematics program there, insist getting MATLAB. But you don't really, Octave is nice for hobbies and also learning stuff if you don't have MATLAB, but it's not really a competitor. It's free though. Okay, so it's free. So let's see, I will just make that AA equals 1 minus 0.5, 0.25. Was that the case? Yes. And then BB is 1 square root of 2. Oops, where is my parenthesis is missing? Square root of 2 and 1. There we go. So those are the same values now here. So the z-plane of this system is something like this. Okay. As you see, it works quite the same. So z-plane is there. The next part is to calculate the impulse response. And for impulse response, let me take a look at the impulse function on Monday. Okay, impulse function, I have NN and then impulse. I'll just copy those and put them here. Yep. And actually I can try check that if this one really is the what I'm looking for. Yeah, it's impulse function. Okay, then we can run this signal, impulse signal, through the system. So impulse response, HH equals filter. Filter is the linear time invariant system implementation in MATLAB. BB, AA, and then the signal int. Okay, there we go. And we can plot that one. Stem NN HH, and we get that's the impulse response. Okay, and now we just check if we have anything after the highest order delay. Our system had the second order delay is the highest. So evidently this is infinite impulse response system. So if there is anything after the second order, the nth delay, where the n is the order number, then it's IIR. Okay, the feedback itself doesn't guarantee that the system would be IIR. The feedback doesn't say anything about it. Yes, you have a question. EER. infinite impulse response system. That's infinite. It goes to infinity and beyond. That one. It never stops. So the response never stops. That's infinite impulse response system. Never goes to zero. It approaches the zero in infinity, but it never gets there. At least I don't have time to wait for that to go to zero. Oh well, you just turn off the power then. Ha ha. Okay, so finite impulse response system would have only those parts, those points in this case, secondary system. Yeah. Good. So, evidently infinite impulse response system, so that one shows it. Then the frequency response. And frequency response. Okay, in here we actually need also the sample rate. Without the sample rate, the frequency response really does not make much sense. Yes, it shows it to be the frequency response in normalized frequency scale. But if you design a filter, it's actually a very practical thing. If you don't know the frequency range where you are using that filter, then my question is, how much do you need? How much do you know about this system at all? So fundamental thing, you need to know the sample rate. Just for fun, I'll put 2000 here, so 2000 samples per second. So this would be some, say, microcontroller-based data logging system, maybe. So there you can actually then calculate the frequency response, BB, AA, the same system coefficients as this far. Then the number of points you want to do the calculations. Use, for example, 1024 is a good number. Not less than 212, 252, 50, no, 254. Again, good idea to use the power of 2 here, since this frequency response is calculated using the discrete Fourier transformation. And for non-2 to the power of something numbers, it will take a little bit longer. You wouldn't see the difference though, but okay. And then the last parameter is the sample rate. Ha! There we go. See, oops, where did it go? That's the frequency response. Wow. You probably got a little bit different because, or did you? It looks, oh yeah, of course. So actually, I ended up having the that 0 point on unit circle. It means that it dips really, really deep on the top, on the magnitude response scale. Now I need to show you something on the whiteboard again. All right, so my frequency response is also something like this. Remember yesterday, the product form of transfer function. E to j omega minus zk and product e to j omega minus pk. Oops. Then you take the amplitude response. B0 divided by A0. On numerator we have k from 1 to n. The absolute value of e to j omega minus zk divided by k from 1 to n e to j omega minus pk. Good. So then on the z-plane, okay, z-plane had levels 3 pi over 4 and 3 pi over 4 in my let's see, that's also in this case 2000 samples per second, so that's 2 pi f divided by 2000. Okay, that comes the frequency of 7500. Oh, 750. Okay. So on that frequency, we actually hit unit circle. So the distance between that one to 0, 1 is 0. Okay, remember we are talking about the point E, J, omega here. And that's moving on the unit circle. When it hits that point, then this distance becomes 0. Okay, what else can we see? Not much. Let me pull this one closer to the unit circle, just to make a point. I will modify a little bit of the system. This is my system, I can do it. Okay. So my, okay, let's see, roots. P equals roots of A, and then absolute value of P 0.5. Let's multiply this one to 0.9. So meaning that now it's in the mid-range here. We move it to the 0.9, so it's only 0.1 distance from the unit circle. I'm just scaling it. PP equals PP times 9 or 5. I think that'll do the trick. Yep. So now I have the on the same angle but different range, and then I need the parameters back. AA equals polynomial, which is defined by these poles P there. New coefficients, which means oh boy, this is not MATLAB. I need to do some clearing. Clear figure. No, it still does it. I do it on figure 2. There, much better. Okay, so those are my new locations of of the zipline on the zeros and poles. Let me do also over again the frequency response. Ah, what happened? Ah, I hit something. um, hmm. BBAA imp. And then stem home to be trigger 3. Huh, invalid command. Okay. This ain't MATLAB. uh, you know what is the easiest way to start over? So I hit something on accidentally and I broke the octave. Yes, you have a question. Uh, so meaning. Oh, that frequency. Okay. Yeah, I kind of. Well, let me do some explanations while I wait for the octave to restart. I think I need a task manager to. Okay, I need a task manager to do here. Where's the task manager? Close window. Close window. Close window. There. I'll just restart the octave here. Meanwhile, some explanations. Oh, right. So we agree that this is actually a distance between this point and that one. On amplitude response, where we have Nyquist frequency here. Okay. For example, if we are right, okay. Let me move. Okay, I'll move those back. I'll move those here. Okay. So if we have, for example, on this point, then omega is 0, which is the physical frequency is 0. So at this point, we calculate the we can calculate this one, basically just this one scaling factor. Then there's a product of e to j omega minus z1 times e to j omega minus z2 divided by e to j omega minus whole 1 times e to j omega minus whole 2. Okay, just eyeballing, that distance is about almost 2, right? 1, 1, that's about the same. 1, okay? 1, a distance to there, another 2. So this one would become 4 divided by, well, that distance is about half, closer to 1, maybe. Well, it's hard to say. But anyways, we have something around, say, 5, number of 5 amplitude response here. 1 point. Another point here. Distance is about roughly, say, 0.7. That one is about 1 point. Something, so maybe that numerator gives me in order of 2. and the denominator actually gives me, well, those are just about the same distance. This distance is just about the same as that, and this distance is same as that. So that is roughly 1. Okay. In that point, 3 pi over 4, which is 750 hertz. This is 0. Distance, because it's exactly at the same point as the 0 on the unit circle. That distance becomes 0. So the amplitude response is 0. In our graph, it was logarithmic, so it means it has minus few hundred dB. Then again, right in here, we have a distance roughly, well, less than 1 on the numerator, and then this one is more than 1, more than almost 2, say. So we have about point here. Yeah, except, well, how about here? Very close to that one. So our denominator is 0.1. So it gets actually, on this amplitude goes over here. Now we can start connecting the dots. So that's how actually the amplitude response kind of relates to this 0 pole plot. So those special points there are the location of 0. Zeros are on IIR system, they are actually located on the unit circle to give the local minimum. You need your suppression of some frequencies exactly on that point. And then these poles are located somewhere closer to the unit circle to add some gain. So that's actually caused by the pole, that gain here, and this one is the 0 of the unit circle. Got it? Simple. Yeah, I know. It's the there's no magic. It just goes like that, right? Frequency response, and when you take the absolute value, it's the amplitude response. You can take this one inside of that product, and that's actually distance. So the numerator is the product of distances to 0 points, and the denominator is actually the product of distances to the poles. Good. Now I can continue. Hopefully, let's see how far I must go. Oh, it really crashed. Just a moment. I'll get my system back up here in a moment. So I have the impulse and I have the system. Can you give the parameters? So this one was 0.9 and was it 0.81 or what are the A parameters? Did you get the AA? AA. You don't have it. Did you start? Oh, that's okay. Good. And the BB was 1 square root of 2, 1. Good. Ah. All right. So the impulse response BBAA imp. Okay. So stem plot the NN and HH looks like that. Now, well, the pole is closer to the unit circle, so it basically have bigger oscillations on that fundamental frequency actually. So the overshoot actually happens on this fundamental frequency. Yeah, I modified the system, that's why it has that one. Okay, so next the frequency response BBAA 1024. Yeah, FS is missing. 2000. The frequency response BBAA 1024 FS, and I'll put that one on figure 2. Hope this one works. Ha ha ha. Yes, it does. Excellent. Then the figure 3. Figure 3 goes for the z-plane of BBAA. All right. So the system frequency response or the impulse response system zeros and poles are here, and then the frequency response looks like that. And as you can see, there's that one notch, meaning the the frequency goes to 0 on that angle 3 pi over 4 right there. And then, so this one is exactly the same as angle of this 0. Okay, and then when I modified the system, now we actually also have some gain. So let's see if I can point into this and do some editing. Can I actually do some editing here? No, it doesn't work. I will plot the amplitude response from to another picture just for fun. So I take the amplitude response, the frequency response. Ooh, wow, what happened? Frequency response FR is same as freq of BBAA 1024 FS. By the way, let's not do it like that. First, help frequency response to see what kind of values I can actually take out from that function. Okay, so if I give it two values, H and W output, then it calculates and returns those values. That's good. So FR equals freq BBAA 1024 FS and not just frequency response, but also the frequencies. There. Good. Now I can plot it. Another figure. 4. Oh, okay. Now I got it. So for some reason, okay, plot. It started waiting for a plot function to follow. FFFR. Wow. Did I break my system again? Oh yes, I did break my system again. Sorry about that. As you can see, you're lucky to have the MATLAB instead of the Octave. But anyways, now I was a little bit smarter, and now I have this Octave, this save, and I can save file and run. What? Undefined. FF undefined. Why it actually give me that? Okay, well, I see. I see. That was in the wrong place. I hate when that happens. Now I got some pictures here. At least 3 pictures. So that one, this one, figure 4. Why it looks like that? Something is strange here. Oh, I see. Ah, okay. What? Of course. It's the real value. This is a complex value, complex number. So this is the real part of the frequency response. Not since complex, the frequency response is a complex number. Plotting it just plots the real number, unless you plot it on the on the body diagram. But basically, this would be almost okay. Not totally okay though. Okay. So what is now missing? You should know it. You will become engineers at one point. It is on linear scale. So that one looks like my picture here, but it's not the frequency response. So frequency response is right. Actually a dB of FR, which is 20 times log of 10 of absolute value of FR. Okay, now we go. That's the amplitude response. And again, figure 4, but dBFR. Better. Okay. I wanted to plot it here since now I can actually select the axis so it zooms it correctly. So there, axis. Okay, where to put the axis? Axis from 0 to 0 to 1000, and from minus 100 is enough to plus 20 dB. I think it's is enough. Well, maybe 30. Okay. Scaling a little bit will show actually that kind of thing. So basically this is a crappy low pass filter. Right. Okay. But anyways, all the features are there. Good. Next step. The group delay. Actually, you can use FDA tool if you wish for the exercises. On MATLAB, there's a nice tool called FDA tool where you can actually do about the same things as in here. Then you basically just use the these system coefficients from the MATLAB space, and then you can start plotting stuff like that. Anyhow, I don't have that luxury, so let me try to find if I have a the group delay somehow here. On Octave, the best place to start looking for help is the Google. Octave group delay. GRP delay, good. On MATLAB, you probably have the same function. Check it. Help group delay. Okay. So it actually shows the group delay, and the usage is the same as on frequency response. Good. So GRFF equals GRP delay of BB AA 1024 points and FS. Wow. Yeah. FS. Setting group delay to 0 at singularity walk. Okay. Good. So it has some singularity points, meaning divide by 0. So basically we can then plot on new figure 5 and plot FF group delay. Ha! So this, if I didn't understand it totally wrong, so this actually shows the group delay in time steps, not, seconds. Check how the MATLAB is actually giving you the numbers. So do you get anything? What is the scale? Do you have the same order of magnitude values on the vertical axis? Or are those milli something? So group delay, and it shows samples. Yes, yes, samples. Does it give us the same value? Yeah. No. No. Yeah, wow, it's a different system. Okay, good. All right. So this is the group delay in samples versus frequency. And as we can see, the frequency, the data, a signal with, for example, 200 hertz would be delayed less than one sample, but then this 350 hertz signal has almost 10 samples group delay there. So not good if you are trying to send a package of information with those two frequencies. They would come out the system at a different time. Okay. But we can actually see the same thing already on the frequency response. So the why I'm working that way? So basically, on the frequency response, the passband is somewhere in here. Hard to tell because of the scaling of this magnitude. By the way, in MATLAB you can also zoom those pictures individually. Just click there and then click zoom, and you can zoom the scale it without the axis command. Okay, so this one does not look too linear. Linear would be straight line. All right. So now I have group delay. I have the this one showing it's a infinite impulse response system. Well, actually, yeah. One figure is missing, but anyways, this also shows that it's infinite impulse response system. The finite impulse response systems would have these poles at the origin, or have a canceling pole, zero at the top of a pole. Remember the 3-point running average or 4-point running average. Let's see. I'll show you some neat stuff just because you are so nice. There are different ways you can actually make the running average system, running average filter. So yn equals the sum of xn minus k, and then basically from k from 0 to n, and then you put 1 over n here. Okay, that's the running average, meaning that you take x of n plus x of n minus 1 plus and so on plus x of n minus n, and divided by 1 over n. And the Argand's diagram would look like something like this. Actually, for 4-point running average, it looks like that. Okay, and the poles are all here. How to make the same system so it's recursive, but still FIR. You take one of those poles right here and also the corresponding, and you cancel it by 0. What did I do here? Did I do something wrong? No, I didn't. But the transfer function comes actually quite nice. You have 1 minus z on the bottom, and then you have, well, you have 1 minus z to the power 4 on the top, meaning that you actually have the difference equation of, well, that also have the 1 over 4 here. 1 over 4 x of n minus x of n minus 4 plus y of n minus 1. Ta-da! Neat, right? So we have some use for the complex numbers and z-plane and that kind of stuff. So, yeah, that's one way of explaining it. Good. So, let's see. Let me go fast and see what I have done here. What kind of damage I have done here. So, stem plotting the impulse response, plotting the frequency response, zeros and poles, at which frequency the system had the highest attenuation, so you need to actually find the frequency. For example, if I want to know what is the, in which frequency I have the highest attenuation in here. Oops. In here. That was plot something. What's the plot about? Figure 4. Yeah. dBFR. I can actually find a couple of things here. Let me see, I'll just Control Z that. So finding the max amplitude response point. We can find the maximum of max dBFR and then ask about the index. Max int equals max of dBFR. So the maximum index is actually 339. That's where my maximum amplitude response is, and then we can actually do FF max int. So on this frequency, I have the highest point of the frequency response. Good. Another thing. Okay. So on that one, I have the maximum. On that frequency, I have the basically it's what is that called? Center frequency of that band pass filter. In other words. Okay, so the lowest one, well, you guess. I think the same works also for minimum. It might work. Okay, and let's see. Another thing, you need to also, on the exercise, you need to scale the system so it has a unity gain at passband, meaning basically that you take this this picture and make it so that that point is actually 0 dB. Okay, meaning on this figure, okay, figure business. You basically the amplitude response should look like, oops, not like that. What did I do? All right. So dBFR should look like dBFR minus the maximum dBFR, right? Then I should have this figure 4 again. No, what the hell is going on here again? This is so frustrating. Does it give me permission to plot anywhere? New figure. No, it doesn't plot me anything anymore. Let me restart it again. Let's see if this helps at all. No, it doesn't. Ha! I had one mistake here, of course. Minus max dBFR. Ha! There we go. Okay. So scaling of the filter means this one. For unity gain, it means that you will scale it such that the maximum amplitude response hits 0 dB, meaning gain of 1. Okay, how to scale the system? This is just the plot. You actually divide the numerator part. So basically, you will be affecting on this value here. You rescale it, rescale this value, meaning that A0, well, it must be 1. So it means that you can scale only the numerator values. So the feed forward values, the BBs. So scaling to unity gain actually means that we take the B parameters and divided by absolute value of frequency response, BBAA 2024, then it doesn't actually make any difference on the sample rate since we are taking just the maximum value. There. Rescaled parameters. Oh, what? What happened here? Oh, haha. Maximum value. Maximum amplitude response. So you divide the current BVAP parameters with the maximum amplitude response. There we go. Then we can do the frequency response again. Well, where was my, there's those plots. Frequency response there. And yes, now it's unity gain system. Good. Okay. So all kind of stuff done for the system. Impulse response, frequency response, scale the frequency response, looking at the zero pole plane, amplitude response, group delay, that kind of stuff. So that's basically the whole thing about this filter analysis. The next step would be actually to go to the quantization effect of the filter coefficients. Unfortunately, the time does not allow me to do it. Then we need some, say, statistical measures. You hate statistics, right? I do. But I have an excuse. You don't. Good. So, next, the spectral analysis of signals. Okay. Now, actually, MATLAB would be nice, since it has the nice tools for getting audio records in and also audio write. You already know how to use the audio write. The easiest way actually to do the audio read in MATLAB would be just double-clicking the WAV file. But let's see, hey, I have a couple of test files here. What? Well, I've tried my luck. Again, open WAV file. Audio data processing. Sound is there. Okay, sound SC is the wave read. Excellent. In MATLAB, there might be also the wave read. So if you find a sound sample somewhere, for example, your previous sound samples, what you have produced, then you can start doing the spectral analysis of that. I have no idea what this test.wave is here, but I will find out. Help. Wave read. Okay. Y, oops, input Y and FS. I don't care about the bits. Wave read, and the file name is test.wave. There we go. Obsolete. That will be removed. Oh, okay. Use audio read. I think the on MATLAB you use audio read anyways, right? What does it say if you say wave read? Let's see the audio read. Well, it's the same. So basically I can audio read much better. Okay, and let's see, sound, YY, FS. That was kind of ding. Good. So the frequency analysis of signal, that was about 1 second long, and the sampling rate here is, what is my FS? 44.1 kilohertz sampling rate. So it's a CD quality audio of ping. So what I can do is, for example, do the old school fast Fourier transform of one section of the data. Spectrum of a selected part of data. I'm lazy. I'm taking the first 1024 points. So I take the subsample x equals the y from 1 to 1024. Okay, first 1024 points. You need to do the last points. You can get the value for the last point by asking the length of the data, and then do some calculus. Okay, and then I can do the fast Fourier transformation of xx. There we go. So that's just FFT of x, which is a complex number. Okay, we need power, the signal power, not the signal amplitude in complex plane. So basically the power of signal xx would be fxx multiplied by the complex conjugate of fxx, or absolute value to the square of 2, so to the power of 2. But this is, you know, old school by definition. Okay, so that's the power spectrum in linear scale. But any power you ever handle, especially on the spectrum, you always handle decibels. So dB pxx equals 10 times log of 10 of that pxx. 10 because the px is already a power in dB. Okay. Now the corresponding frequencies. Okay, what did I say about the frequency scale? So now basically we have divided that 1024 data points into exactly 1024 data points in frequencies axis, where our the 1024th point would be actually the sample rate. Okay, so that's your scaling right there. So if you want to calculate what are the corresponding frequencies, the real frequencies, you have data from 0 to 1023. 0 is the first frequency, so offset by that one, divided by 1024. multiplied by sample rate. Good. And we are interested only on first half of those values, since the second half is just, the lower part of this complex plane. So this is already from 0 to Nyquist frequency. There. Now we can plot it. New figure. Plot FF ins and dB dxx ins. And let's see if it breaks or not. It didn't break. It didn't break at all. So that's how my signal looks like. So if you wondered why we can still hear the sound, although I had quite much there, the noise, is because you have that one peak there, way above the frequency, the noise. So noise is that flat thing that looks like noise. Good. What else? Okay. Remember, do you know how your ear actually functions? Did I show you it already, or was it in Japan? So your hearing element has some basically tuned hairs on it, each for certain frequency, and your brain is quite nice handling the frequency. So basically, you have Fourier Transformation in your brain. That's how you recognize different voices, not by time, but by frequency, because the sensing element is actually sensing the frequency of whatever you're hearing. And right now we are tuned that ping sound into one of those elements in your ear. Okay, that was some trivia. So next time you go to, eat some tapas and drink cerveza, you can brag to your friends at the late hours of the night. Let them know. Okay. So, yes. So Spectral Analyzer actually shows that we have this. Can I actually do the? No, I cannot. Let me do the scaling of this picture again by saying the axis command 0, maybe 1000 hertz, then 0 dB to 50 dB there. Haha. So that's the zoomed. You can zoom by, with the mouse. But anyways, as you can see, it's kind of rough estimate of the spectrum. Well, our spectral resolution is actually Fs over the number of samples. 1024 samples, and we have 44.1 kilohertz. So actually we have 44k divided by 1k is about 44 hertz between two samples, or the two frequencies there. So it's a rough estimate. If you need more precise spectral resolution, you just need more samples. Okay, there we go. So, yeah, that was a spectral response. The last one is the spectrogram, meaning the whole image of this signal. And now you have different, you actually have something different than I. You have spectrogram, but I think I have spectrogram. Yes, I have the old-fashioned. They are somewhat the same, but not the exactly. We'll see. Ah, spectrogram. I need to put the help in my other window here. So this one actually draws also the image. So your command was spectrogram, not spectrogram. Just the data, the whole data. Then how many points? 1024 points, for example. Oh, this is quite much. I think, say, maybe 256 is enough, or maybe 512, as long as it's 2 to the power something. The next parameter is actually the windows. Okay. In your case, you have different places for the parameters. In your case, you will write spectrogram. Okay. Why that one? And then the next would be the overlap, right? Following by the window size, or was it the vice versa? But anyways, those are the values what you would use. Then you have the sample rate. Then you would have y-axis. Okay, you try that one. I don't. I have octave. It looks like, in my case, I need to use specgram. Why? 56 sample rate. Sample rate, window size, overlap, and then the y-axis. Or do I need to do the y-axis? No, I don't need to do the y-axis. You need to do the upper part. This is how I do it. Control-C detected. Okay, good. There. That's the spectrogram. So, when you have, so basically this is an image, and you set the parameters so that this image will be the one you will show to the these business managers on the company. So this is not science. Image is almost always such a representation, and whenever it's clear enough and looks nice, then it's done. If you take more or a smaller window size, then basically you will start having less pixels on the frequency scale. But if you take too big frequency response, frequency resolution, then basically you are losing on the time, unless you are doing overlapping more. Okay, but as I said, this is a picture, and you have some parameters to tweak it so it would look nice. And this one actually shows our, well, I think it was the 440 hertz frequency signal. Let me take a look. Oh, no, I don't have it anymore here. But anyways, that's my 440 hertz from Monday. Maybe. Ding. Right? So basically, that's the exponential decay of the signal showing on the time scale. And that just shows, okay, I had some, some signal on that frequency on that price. Okay. It's very so bad, actually. So, the MATLAB, actually, the spectrogram function, unfortunately, was designed by some mathematician who doesn't know about which are how to put the axis. By default, it puts time axis vertical, starting from 0 here, and the frequency axis there. So for engineers, it doesn't make any sense. It would make sense if actually it would be kind of waterfall, kind of so 0 and the time flowing like that. Then it would be like a waterfall, but not like what they have done in there. So you have been warned. Good. So I will just go quickly on my this one, and okay, yeah. So that was all for today's topic. Yes.
Question 7. I don't know how to create with the time difference.
Wait a minute. Do I have the start frequency 200 hertz, end frequency? Yes, I have this one. Sorry. I will show you. I'm not showing you everything. The easiest way, that is also called chirp. Help chirp. That's the easiest way. But since you asked, by the way, your classes is starting quite soon, I think. Since you asked, I will actually give you a short lecture about frequency. What is frequency? What is frequency? What is frequency? Let's start from sine wave. So if our signal is sine 2 pi f times t, that's quite simple. That is the frequency. It's a constant frequency. Okay, but how about a function like sine of 2 pi g of t? What is the frequency? How to calculate the frequency of this kind of signal when you have the generating polynomial or whatever here? The frequency of this signal would be okay. Well, compare to this one. So if you have the GT is actually GT is f times t, then it means that the dgt divided by sorry. Yes, dt. Yes, dt equals f, just constant. So basically, if you want to generate a signal with the varying frequency, you need to plug in on this sine 2 pi ft an integral of that. So in case of chirp, you have a linear signal like that. You have f1, f2, that's the same time 0. So basically, there you have the delta f. So ft would be f1 plus, well, f2 minus f1 divided by that time t times time. Okay. And you integrate that. This one gives constant, right? dt plus f2 minus f1 divided by t. So this is also constant t dt. See, there is a trick. So that gives me f times t plus, well, constant f2 minus f1 t squared divided by 2. Right. Say right. Okay. But I recommend actually using the chirp signal there. But if you want to generate any signal in a MATLAB environment, you know, for example, that you would actually plug in the modulating frequency here and some sort of that kind of well, the frequency what you want on DG, and then do numerical integration, a cumulative numerical integration, and then plug that one inside of psi. I can show you that one in a moment. On Octave, yes, it does work. Good. There we go. Generating funny sounds. So first I will take the sample points 1 to 40. Well, I have the fs somewhere. Okay. Divided by fs. So this is 1 second long. The time vector with the sampling rate of fs. And my fs here is, I think it's for 44.1. Yes, good. That'll work. Sample time vector. Then I want, for example, a kind of undulating sound, like an ambulance does. So my center frequency would be about 1000 hertz, and that would change about twice a second, not faster than that. So my GT is sine of 2 times pi times 2 times a second times t, and with the amplitude of, say, 500 hertz, and with offset, okay, of 1 kilohertz. And it looks like, do I have any figures? No. Plot TT GT. Okay, looks like that. So, wow, that that looks really funny. So this signal is actually changing like this twice a second, around 1,000 hertz plus minus 500 hertz. So something like that. Let's see how close I will get it. And the trick is to do the numerical integration of that one and do the cumulative numerical integration, which basically means sum. Okay. So ft equals. I need to also just for fun, I need to check the function reference manual for this one. Where do I find it? Function list alphabetical. C. Sum. Cumulative sum of elements. Or trapezoidal. Numerical integration of points y using trapezoidal method. Okay, let's see. There I can. That's even better. Cumulative trapezoidal of GT versus T. Yes, X and Y. So numerical integration. Okay, so not just any integration one, cumulative integration. And then this is ready to go inside of sine of 2 pi. Just that GT. No T is required anymore. It's already inside of this one. So my signal S is maybe a little bit less amplitude, sine of 2 times pi times G, not GT, FT. And let's see, sound SS. Sampling rate is not right. I forgot to put the sampling rate. Oh, yeah. So that's the mechanism. Whatever this behavior of your the frequency behavior would be, so that's F, that's T. If you even want smiley face, you just generate the function that gives you smiley face on frequency space. I give extra points if you can. Actually, you would do 1, 2, 3, 4, 5, and actually 6 and 7 different generating functions and integrate those and sum the products at the output. That will do the smiley face sound. That's actually nice on the telephone. Smiley face. Yeah. Another, thing to brag about when you go with your friends to get tapas. And after 8 services. Good. Yeah. So that's all for today. I will be trying to save everything what I did and make some comments. Unfortunately, well, my MATLAB stopped working sometime Monday, maybe, since it was working on week ago Monday. So this license has expired. But anyways, so that was today. Tomorrow we'll have again the laboratory L1, and the topic is finite impulse response filter design. Good stuff again. Okay,